So this is lab number 2, transformer modeling. So your coursework consists of 2 labs. First one, lab 1 is power factor correction, which you have completed previously. This is lab number 2, transformer modeling. Okay, so first of all, we'll take a look at how this lab will be conducted. So this lab will consist of 2 parts, right? One will be the preparation of the answer sheet. So before we are doing this lab, we have to prepare some theoretical calculation. So that will be done in day number 1. Then the laboratory simulation or the MATLAB simulation will be done at day number 2. So the first day we will do how can we prepare the answer sheet before doing the laboratory simulation in next day. So we'll take a look at this one, preparation answer sheet, which consists of theoretical calculations. So if you see your lab, you will see in a preparation, the first one is the values of R and L in the load for both series and parallel connections to achieve the load conditions. So load conditions are given S equal 10 kVA and the power factor is 0.9, and remember this power factor is most of the time the given load is inductive load, right? So therefore this power factor is 0.9. Actually this power factor is lagging, not leading, lagging means we have inductive load. Okay, so that's why when you were given the load consists of R and L, so you should be able to understand this power factor is lagging, and you have to find value of R using active power values and value of L using the reactive power values. Okay, so first you will see the calculation area. In this calculation area, before we are going to calculate the load, right, in both parallel and series, we have to do few calculations. So we have to find, we were given VRMS, so we have to identify the load. So the load will have VRMS of 415 load. So this is the voltage for the load, right? And from that one we can find the active power P. Active power P is equal to S multiplied by the power factor. So you can find the active power P. Then from that one you can find the reactive power Q. Reactive power Q is equal to S squared minus P squared and the square root of the whole thing. So from that one you can find P and Q. So like this you can find P and Q. So as you know, if you have found the active power which is P and the reactive power Q, then you can find the resistive component and the inductive component. That means you can find R and L, right? So here you are given the load can be in both series and parallel. Therefore we have when you have P and Q, you can either calculate the load for series R and L and or parallel R and L. Then if you want to find the current, right, actually for this one you will be needing to find the current. So IRMS is equal to S divided by VRMS, because S is equal to VRMS into IRMS. So these are the pre-values that we are going to calculate before going into calculate the load. So calculations for R and L series, that means when the resistor and the inductor consist of the series connection. So this is how it looks like here. I think you can remember when I have told you previously, when you have a series combination, what you are going to do is, if you were given the value of active power P and the reactive power Q, in order to calculate the resistance and the reactance, you are going to use the current value, right? Because the same current will go through both resistor and the inductor. Okay, so therefore we have used, so P we have found previously, therefore R is equal to directly P divided by I squared. Okay, so like this, since we have found Q, right? Since we have found Q, Q also we can, when we have Q, L is equal to Q divided by omega I squared, right? So, or else if I simplify this one, if I simplify this one, first of all, you can find X. X means the reactance. Reactance X is equal to Q divided by I squared. Right? X is equal to Q divided by I squared, and X for an inductor, that is equal to omega L. Omega L means 2 pi FL. So after substituting this in here, L is equal to Q divided by omega I squared directly. Okay, so I'm not going to clarify this thing too much because we have done the same calculation, right, in your lab 1 as well. Okay, so next one is to find it for the resistor and the inductor when it is in parallel connection. So when it is in the parallel connection, I have told you, if you have already found the value of active power P and the reactive power Q, what you have to use is, in order to find the resistance and the reactance, the voltage value, right? Because when two when R and L in parallel, they will both at the same voltage since they are in parallel. Equal to Vrms squared divided by P. Okay, R is equal to Vrms squared divided by P. So directly we can find the resistance value of R. And likewise we can find the value of L. L is equal to Vrms squared divided by omega Q. So again, this thing we can find it like this. So let's say the reactance X is equal to Vrms squared divided by Q, right? And X is equal to omega into L. Omega L means 2 pi FL. So combining both together, we can write L is equal to Vrms squared divided by omega Q. So therefore we can find for R and L parallel. Okay, so remember this calculation. So this load finding calculation, this is before we are starting the transformer. So this is the load that we are connecting to the transformer at the secondary site. Okay, so now we will go on to the given. So then you were given the transformer data at the beginning of the lab, right? Transformer. This is about the transformer. Transformer is, it is as it given 10 kVA. 10 kVA means the rated apparent power, which is S, right? S is equal to 10 kVA, and it is single phase. So the transformer will have only one phase, right? And 11 kilovolt RMS to 415 volt RMS, and it is working at 50 Hz. So this 11 kilovolt RMS and 415 volt RMS, this is given in order to calculate the turns ratio. So if you can remember, what is turns ratio? Turns ratio is primary voltage divided by the secondary voltage. So as you can see it in here, the primary voltage level, that will be at 11 kilovolts, right? And the secondary voltage will be at 415 volts. So we can identify in here, primary means actually it is the high voltage side. So secondary is actually it is the low voltage side. So you can see 11 kilovolts is larger than 400 volts. So therefore high voltage side is the primary, 415 volts is the secondary. Okay, so this is actually used in order to calculate the turns ratio. Okay, we were given test data, right? So in test data, actually I have explained in the tutorial also, when you have a transformer, in order to determine transformer parameters, we are going to perform two tests, right? What are those two tests? That is the open circuit test and the short circuit test, right? So you can use in the transformer open circuit test, if you can remember, you can determine RM and XM or LM, right? Or using the short circuit test, you can determine the series resistance and the reactance, or else the inductance, right? So there are two tests, and you were given the data for that. This is the open circuit test. So as I have explained during the tutorial, so please refer the tutorial before doing this lab, right? So in open circuit test, right, what you are doing is you are going to open circuit the output side. So output side means the secondary side. So you will open circuit the output side, then you are going to take the measurements, right? So in here, what you have got is, when you open circuit output at the secondary, the voltage is 415 volts RMS. At secondary, 415 volts RMS at when you are doing the open circuit test, right? So therefore that means there won't be any current or voltage going through the there won't be any current going through the load. So therefore there at the secondary side you will have the 415 volts, and when you have 415 volts at the secondary side, at the primary side you will have 11 kilovolts, because here you are given that 11 kilovolts to 415 volts. So when the output is at 415 volts, then in the primary side it is equal to actually 11 kilovolts. So 11 kilovolts will present as 415 volts at the output. Then current value were given 530 milliamperes. Then the power, which is 100 volts, right? So here consider this, in this current is equal to 530 milliamperes, and it is given as a peak value. So when you are doing the power calculation, so as you remember, right, you will always use the RMS value. So therefore you have to divide this 530 by root 2 in order to get the RMS value, right? So the next test is the short circuit test, right? In the short circuit test, what you are doing is you will short circuit the load, right? You will short circuit the load, then you are measure the input voltage. So VS, this short circuit voltage 33.2, that is actually the voltage that you are seeing from the primary side, because output you cannot find the voltage because it is already short circuit, right? Then the short circuit current, that is equal to 24.1 amperes peak. Again peak, in order to calculate the RMS you have to divide by root 2. Then the power, you can see it is 250 volts, right? 250 volts. So as you have done in your lectures, right? So these power values are measured using the wattmeters, right? Using the wattmeter. So refer the diagram given in your lab sheet also in order to get a good understanding about these readings, right? Or else actually this thing you can understand um, by if you refer the previous the tutorial that I have done previously. Okay, load data. So when you have a load, that means when you are doing the open circuit test and the short circuit test, there won't be a load, because in open circuit test you are going to remove the load, which means open circuit, uh, and the short circuit test what you are going to do is again you will remove the load and you will short circuit the two ends, right? So when you are doing open circuit test and the short circuit test, there won't be a load, right? But if you are going to connect the load for this one, this is the load that you can connect, because this is the load you are given, right? The actual load will be 10 kVA at 0.9 power factor and 450 volt RMS through that load, right? So the load calculations that we have done previously, we will be needing it when we are doing the MATLAB simulation. But here, in order to calculate the transform parameters, you don't need, right? Transform parameters, you don't need the load data. You only need the test data. Okay. First of all, we'll take open circuit test. So if you can remember, in open circuit test, right, R dash and X dash, R dash and, so refer the diagram, R dash and X dash, that is, they are the series values, right? So they are the series values. So when you open circuit them, right, open circuit the transformer, there won't be any current going through R dash and X dash, right? So therefore only thing present will be Rm and Xm. So refer my tutorial also, right? Rm and Xm, which will be at the shunt resistance and the reactance, right? So these are the open circuit data. So consider this 415 volt RMS means that is the secondary voltage value. So because open circuit test means we are open circuit in the secondary or the output side, therefore 415 volts is the output voltage. When you are doing the calculations, you have to convert it to the primary side. So when we are converting the primary side, 415 volts will be converted as 11 kilovolts, because primary side voltage divided by secondary side voltage is equal to turns ratio, and turns ratio is equal to 400 so 11 kilovolts divided by 415. Therefore when you are converting it to the this 415 volt RMS to the primary side, it will be 11 kilovolts. So in open circuit test, open circuit voltage, VOC means open circuit voltage, that should be used as 11 kilovolts, not as 415 volts, right? Therefore, so we were having the value of P, and also, right, and also this Rm and Xm, right? If you so refer the diagram also, they are placed in parallel, right? Rm and Xm. So therefore when Rm and Xm parallel, and you are given the value of power value, P value. So if you are given the P value, you are going to use the voltage value in order to calculate the using the voltage value you can calculate the resistance. So Rm, this is equal to V open circuit square divided by capital P. Okay, so likewise you can likewise you can calculate the Xm value also, right? Xm value will be open circuit voltage squared divided by Q. So we need to find the value of Q. Q means reactive power by the inductive or the reactive part, right? So in order to do that, we have to find S, because Q we can find using S and P. So S is equal to open circuit voltage multiplied by open circuit current. So in here means for both equations, right, VOC is equal to 11 kilovolts, right, 11 kilovolts. Okay, and IOC, that is equal to 500, not 530 milliamperes, 530 milliamperes divided by root 2, because IOC is here. This is the RMS current, right? So using these P and S values, you can find Q, right? So if you have Q, you can find Xn, right? So again, V squared is V squared means VOC squared, right? VOC squared and divided by Q. Again, it is 11 kilovolts, right? And so Xm you can find. So if you have found Xm, you know that this Xm, that is inductive part. So therefore, you can find Lm in this equation, right? So we can find Rm and Lm. Okay. So frequency will be 50 hertz, right? So likewise, you have found Rm and Lm. Okay. Then the next one is the short circuit test, right? So doing the short circuit test, what you can do is you can find the two series resistance and the reactance, which is R dash and X dash. So the short circuit test data. Uh, so uh, so again, right, when we short circuit, output will be short circuited. So if you can remember, in the tutorial I have shown you, when it is short circuited, since Rm and Xm value are very high, all the current will flow through R dash and X dash. So in the tutorial I may have used different symbol for R dash and X dash, but they will be the same thing, right? Same thing. So R dash and X dash, the current will be going through R dash and X dash. There won't be any current going through Rm and Xm. So therefore we can exclude Rm and Xm, that shunt part we can exclude from the circuit. So we can remove that thing, right? So in this circuit we have only R dash and X dash. Okay. So you are given the short circuit voltage and the short circuit current and the power also. So remember, R dash and X dash, they are the series components. So therefore what you are going to use is the current, right? So R dash is directly P divided by I squared, right? So short circuit current, short circuit current squared. So again, here you can see 24.1 I short circuit, that is the peak current. So you have to divide by root 2 before substituting to this equation. So P is equal to 250 watts. So therefore you can calculate R dash. Then in order to find X dash, you have to find Q. So how to find Q? By using S. S is equal to V short circuit multiplied by I short circuit. So which is 33.2 multiplied by short circuit RMS current. So you have to calculate RMS current, right? So therefore you can find S. So if you have found S, you can find Q. Q is equal to square root squared minus P squared. Then you can find X dash, which is Q divided by I short circuit squared, right? So again, that X dash component, it will be an inductive part. So therefore X dash is actually 2 phi F L dash. Let's say 2 phi F L dash. So substituting for X dash 2 phi F L dash, so you can find L dash like this, X dash divided by 2 phi F. Okay. So likewise, we have found Rm, Xm. From Xm we have found Lm, right? Then R dash, X dash. From X dash we have found L dash. So those are the basic parameters of the transformer. So we have found those parameters in here, right? Then there's another thing that you need to find. So it is very much easy. This is a repetition of the transformer data, which is given as 10 kVA, 10 kVA single phase, 11 volts to 415 volts, 50 hertz. So what you have to do is you just need to divide primary voltage divided by should be divided by the secondary voltage. So according to this one, primary voltage is the high voltage side, therefore I have it as high voltage, then divided by low voltage, 11 kilovolt divided by 415 volts. So likewise you can find this turn ratio. So that is what you have to do for the first day of lab number 2, right? So complete your complete only this part, right? Not the next part, only this part, calculations up to this point, right? Then you have to do a submission. You have to do a submission from the progress that you have done for today's session. So remember, you don't need you don't have to do you don't need to do the MATLAB part, right? So if you can open the MATLAB, you can just open it and see what is the values and what will happen in there, right? But actually that is for the next day number 2. So only complete up to this point as the day 1 of lab number 2.